The Dirichlet distribution, which we shall just touch upon in this course, is defined like this. So this definition, of course, looks rather complicated and not at all well motivated, but it's a good idea to start with the definition. So first of all, it's a multivariate distribution, x1 to xp. Their joint distribution is called Dirichlet. So I have just abbreviated it to DIR. The complete spelling is this. This T is silent, so it is Dirichlet, not Dirichlet. And there are these parameters. All the parameters are strictly positive. So the first thing to notice here is that I have only p many random variables and p plus 1 parameters. Now when I make this statement, I mean that this has joint density, which is given by this complicated stuff, but just observe where this thing is non-zero, all the xi's are positive and their total is less than 1. So let's start by understanding this support. If p equal to 1, in that case we have just x1, so it is actually a univariate distribution. In that case, the condition is that this must be positive and the sum, which is just itself, must be less than 1, which means it must lie between 0 to 1. So the support is this unit interval. If p equal to 2, then it's a good idea to draw a little graph showing x1 and x2. Then the condition that x1 plus x2 less than 1 means the support is this little triangle. If we have p equal to 3, we have x1, x2, x3. In that case, it is this tetrahedral region with vertices 1, 0, 0, 0, 1, 0, 0, 0, 1 and 0, 0, 0. A good way of having an intuitive feel about this set for any dimension p is to think of this vector as a probability vector. So the Dirichlet distribution is a distribution on the set of all probability vectors of a given length. Now I should qualify that statement a little, because it is not yet a probability vector if I consider x1 to xp, because the sum is less than 1, so it is this comma 1 minus x1 minus x2 xp, that entire thing will be a probability vector. Now we should of course check that this is really a density. I merely wrote something down and claimed that this is density. In order for this to be density, we have to check that this is always non-negative, which it obviously is because of this condition. But is the integral finite? Well, I am always integrating it over a nice bounded region. This function is continuous, so there should not be any problem as long as this function itself is bounded. Now, if all your ai's are greater than 1, in that case, or greater than or equal to 1, in that case all these things are bounded quantities. So the integral exists and it is some finite quantity, so you can find out such a constant. However, if at least one ai is less than 1, then that corresponding exponent will become negative. So as for example xi comes arbitrarily close to 0, this will shoot up towards infinity. In that case it will be an unbounded function and one needs to apply suitable checks. Not very difficult, but we shall skip that in this course, and to show that it will still be a finite integral. We have this condition that all the ai's are greater than 0, and we have actually seen this argument in a real analysis course because this is very much like the beta density. So the same argument works here also. The first important theorem is very trivial to prove. It says that suppose you start with a Dirichlet distribution like this. Now what I do is I want to permute them in any order. Just to give you an example, Suppose I have p equal to 3. Now what I want to do is, I want to just permute them. Suppose I make this 3, make this 1, and make this 2. The same 1, 2, 3, but in a different order. Then this will also change exactly in the same way. So this will become 3, this will become 1, and this will become 2, and the last one will remain untouched. Just try your hand at it. It is super trivial to prove. You can just write down the distribution function of the original one and the changed one. You will see that this just trivially the same permutation is also occurring here, or you may use the Jacobian transform. Then the Jacobian matrix is just a permutation matrix, so its determinant of a permutation matrix is plus or minus 1. When you take absolute value, it is 1, and you will get it very trivial. So to state it as a general theorem, we start with pi, any permutation of the indices 1 to p. This pi has nothing to do with 3.14 or anything. It's just a 1, 1 onto function from 1 to p to itself. X pi 1 up to x pi p, that is permuted, will be having distribution the same as but permuted exactly according to pi, and the last one will remain unchanged. As I said, the proof is very easy. Try your hand at that. The second theorem, which is a little less trivial to prove, but still it is straightforward, says that suppose I start with x1 to xp, again Dirichlet, but this time I have written things a bit more explicitly, ap minus 1, ap plus 1. Now suppose I want you to keep only the first p minus 1 of them. So I just make this minus 1. So I will write it afresh. So the marginal distribution of the first p minus 1 will again be, you have guessed it, another Dirichlet. But now the dimension has gone down. Earlier I had p things here, so p plus 1 things here. Now I have p minus 1 things here, so I am going to have only p things here. And they will be, the first p minus 1 will be exactly copied from here, because the first p minus 1 are taken down here. Then these two will get added up and serve as the last parameter, ap plus a p plus 1. And you can immediately see the pattern by applying the same thing again on this. If it is x1 to xp minus 2, it will be a1 to ap minus 2, and p minus 1, p and p plus 1 all will be added together. And you can go on doing it until the very last step. Now I shall give you a quick hint about how to go about proving this. Here you have to integrate over xp. That is obvious. So it will be a dxp, and you will write that huge joint density over here. The question is, what should be the limit of the integration? Remember, the condition is on xp is that xp must be greater than 0, and summation of all these things must be less than 1. When I write it as a condition on xp alone, it looks like xp is less than 1 minus x1, etc. minus xp minus 1. So you can guess that the integral will start from 0, go on up to 1 minus x1, xp minus 1, and this integral. And in this integral, most of the things are actually free of xp, they will come out. There are only two terms that will involve xp. One of them will be xp to the power ap minus 1, and the other is 1 minus minus. One of them will be xp and xp plus 1 minus 1. So essentially it will be very much like a beta integral. Once you divide by something such that the integral becomes 0 to 1, it is pretty straightforward. You should try to do that. Now we shall start worrying about that constant that we wrote in that Dirichlet distribution. But first observe this very simple thing. If x1 has Dirichlet a1, a2, notice that this is same as saying x1 actually has beta a1 a2 distribution. Now from this we can get our first guess about what that constant will be, because in case of beta we know what that constant is. The constant was this. Of course, when x1 lies between 0 to 1 and 0 otherwise, so this was the constant. Now from this it should not be very difficult to guess that if you work with Dirichlet A1 to AP, then the constant should be gamma of the total A1 to AP. So here I am stopping at AP. Well, if I can make it AP plus 1, it doesn't really matter, because here I am writing in general AP plus 1, and here also AP plus 1. Then you are dividing by all the individual gammas. Now how do you really go about proving it? Well, in the same way as we proved the second theorem, you can just apply that result by folding step by step. Of course, you will have to do it only once, and then by induction, you will arrive at this formula.